Hello and welcome to this advanced high rotational dynamics talk on angular momentum. The angular momentum of an object is a very useful and importantly property in rotational dynamics, similar to linear momentum in linear motion. There's a particle opposite of mass m and it's rotating about the axis O. Its linear momentum, p, would be mv, mass times velocity. The moment of momentum is mv times r. L is mvr, where r is the perpendicular distance from O to the direction of v. The angular momentum of a particle, L, is equal to mvr, which if we replace v with v equals r omega, that gives us m r omega r. So hence the angular momentum of the particle is mr squared times omega, mass times the square of the radius times your angular velocity. For an extended rigid object, so anything other than a point, then your angular momentum is the sum of all those angular momentum, giving the sum of mr squared omega, or omega is a sum of your mr squared, because omega must be the same for all particles. All particles on your rotating object must be rotating at the same angular velocity. But we know that the sum of mr squared is equal to I, the moment of inertia. So by substitution, we can say that L of your rigid object is equal to I omega. Now, the units of L, angular momentum, is kilograms square meters per second. And recall that because the radian is dimensionless, we don't include it in our units. Notice the use of the term rigid. For a rigid object, all the individual particles will have the same angular velocity. So the angular momentum, like momentum, is a vector quantity. What's difficult to understand is the direction of that vector, and the direction of your angular momentum is actually at right angles to the plane containing v and r. So in this case, it's through the angle of rotation. So in the example above, angular momentum is actually out of the page, passing through this point O. In linear dynamics, you should be aware that there's a law of conservation of linear momentum, which applies in the absence of external forces. So we know that in the absence of external forces, total momentum before is equal to the total momentum after. So there's something very, very similar in the rotational dynamics. There's an equally important law which states, in the law of conservation of angular momentum, in the absence of external torques, angular momentum is conserved about a given axis. In problems involving rotating objects in the absence of external torques, we can use total angular momentum before is equal to your total angular momentum after. Here we've got a boy swinging on a chair. He's swinging at 1.5 revolutions per second with his arms outstretched. When he draws his arms in, his moment of inertia falls to 0.6 of its initial value. What's going to happen to his rate of spin? Pause the video and discuss that now. Because angular momentum at the start is equal to the angular momentum with the arms in, using L equals I omega, I times 1.5 must equal 0.6 I times omega. Your i's will cancel, giving you omega is 2.5 revolutions per second. Notice that there's no need to change the units of angular velocity, so it's just about ratios. Here we've got the same animation, slightly bigger. The person is sitting on a rotating chair, holding a 2 kilogram mass in each hand at arm's length. Again, you should be able to use a stopwatch and calculate the angular velocity. Going to draw the arms in. You could calculate the new angular velocity. Out and in. Obviously, this is ignoring any frictional torque. An example problem. A roundabout has a moment of inertia of 250 kilograms square meter, about a vertical axis through its center and a radius of 1.6 meters. A boy of mass 50 kilograms is hanging from a branch of a tree overhanging the roundabout. When the roundabout is rotating at 20 revolutions per minute, the boy drops off the branch and lands near the rim of the roundabout. What is the angular momentum in the horizontal plane of the boy just before he lands on the moving roundabout? Pause the video, try that one yourself. The angular momentum of the boy is 0 in the horizontal plane, since he has no velocity or component of velocity in this plane. Determine the angular velocity of the roundabout just before the boy lands. State any assumptions you have made. And the total angular momentum before is equal to the total angular momentum after. So when you substitute that in, that gives you an angular velocity of 1.39 radians per second. The assumptions you've made are that there are no external torques, as in the conservation of angular momentum law, and the boy drops directly vertically onto that roundabout, so he has no horizontal component of velocity, which would then mean that it would be affecting his results. Rotational kinetic energy. The linear kinetic energy of an object moving with velocity v is Ek equals half mv squared. A rigid object may also have rotational kinetic energy due to its rotation. And again, you can see the similarity between these equations. With rotational kinetic energy is half I omega squared, where rotational kinetic energy is still measured in joules. A rigid object rolling down a plane will have both linear kinetic energy and rotational kinetic energy. Hence, problems involving the conservation of energy law must include rotational kinetic energy as well as your linear kinetic energy. Let's have a look at this example. The change in gravitational potential energy is EP, is mgh. The mass is 2.4. The gravitational field strength or acceleration due to gravity 9.8 meters per second squared times by 0.6 sine 40, which is the vertical height of the slope. Applying the law of conservation of energy, the gravitational potential energy must equal your change in linear kinetic energy plus your change in rotational kinetic energy. Both were assumed to be 0 at the top. We've obviously got too many unknowns, but we know that omega is v, value of v is equal to 2.3 meters per second. We're assuming that no energy is transferred to heat or sound and no slipping occurs. So the object rotates fully down the slope and it doesn't slide down the slope. Let's have a look at the example problem. A flywheel, W, rotates about a horizontal axis of a friction-free bearing. A length of rope is attached to a 3 kilogram mass, and 1.2 meters of this rope is wrapped around the axle. The surplus rope hangs vertically as shown. The system is stationary, and then the mass is released. The moment of inertia of the flywheel and axle is 0.78 kilograms square meter. The radius of the axle is 20 millimeters. Calculate the change in potential energy from the time the mass is released to the time the rope is completely unwound, which is there. Well, your change in EP is mgh, which is 3 times 9.8 times 1.2, which is 35 joules. Calculate the angular velocity of the wheel and axle when the rope is completely unwound. Using the conservation of energy, EP equals change in EK plus your change in rotational kinetic energy. So that's 35 is equal to half mv squared plus half I omega squared. Again, substituting V 9.5 radians per second. Determine the angular acceleration of the flywheel after the mass is released. The initial angular velocity is 0. The final angular velocity is 9.5. The angular displacement of the axle as the rope uncoils is theta, which is 2 pi times by the length of the rope over the circumference. This gives us 60 radians as the angular displacement. Substituting that in for our equations of motion, omega squared equals omega naught squared plus 2 alpha theta, we get an angular acceleration of 0.75 radians per second squared. Let's just go over and compare our linear and rotational quantities, see how similar they are. It could be helpful to relate the rotational quantities to their linear counterparts. For example, the linear displacement is comparable to the rotational angular displacement. In opposition to change in linear motion, which is a mass or inertia, has its rotational counterpart in moment of inertia, which opposes the changes in rotational motion. The word moment in this context implies a turning effect. Hence, the torque is sometimes called the moment of force. Angular momentum may be referred to the moment of momentum. So to convert a linear quantity to its rotational counterpart, you multiply by r, which gives us in linear, v squared equals u squared plus 2as, s equals ut plus half at squared, and v equals u plus at. Our rotational equivalent, omega squared equals omega naught squared plus 2 alpha theta. Theta equals omega naught t plus half alpha t squared, and omega equals omega naught plus alpha t. In dynamics, we can replace F with our torque, mass with your moment of inertia, which gives us F equals ma, becomes T equals I alpha, P equals mv becomes L equals I omega, and EK equals half mv squared becomes E rotational equals half I omega squared. Let's try the summary. If you want to pause the video and try filling it in, and I'll see if I can do the 14 blanks for you. Count how many you get right. The torque T is the tendency of a force to cause or change rotational motion of an object and is equal to the force multiplied by the distance r of the line of action of the force from the turning point. So it has to be perpendicular. The unit of torque is the Newton meter. The moment of inertia of an object about the axis depends on its total mass and the distribution of mass about the axis. An unbalanced torque produces an angular acceleration, alpha, and the angular acceleration varies directly with the unbalanced torque. Since T equals I alpha, the angular momentum L of a particle about its axis equals its linear momentum multiplied by the distance to that axis. In other words, L equals mvr. For a rigid object, it equals the moment of inertia about the axis multiplied by its angular velocity. L equals I omega. In the absence of external torques, the angular momentum of a rotating system is conserved. The rotational kinetic energy of a rigid object is given by EK rotation equals half I omega squared. When applying conservation of energy, linear or translational and rotational kinetic energy must be taken into account.